Semi-supervised learning is a promising method for mining information in limited labeled data. In this work, we propose a mutual correction framework named MCF for semi-supervised segmentation of medical images. Although the current methods based on convolutional neural networks have made great progress in various fields of image processing, the cognitive bias of the model hinders further performance improvement, especially in semi-supervised scenarios with scarce labeled data. The cognitive bias greatly affects the quality of pseudolabels. Many works have demonstrated that convolutional neural networks have a very strong learning ability, but at the same time we observe that their ability to correct their own cognitive biases is weak. Inspired by the idea of contrast, we exploit the interactions between different subnetworks to guide the networks to correct each other. The consistency regularization methods based on mean teacher is the mainstream method in the current semi-supervised medical image segmentation. They have three characteristics: subnetworks with shared structure, parameter update method of EMA, and consistency regularization. The first two features force the model to output the same predictions, making training more stable. The latter feature provides a supervisory signal for unlabeled data. However, there are also three corresponding disadvantages contained therein. The shared structure reduces model diversity. The EMA update method makes the performance of the teacher model limited by the student model. Finally, the consistency regularization propagates the cognitive bias of the model into the pseudolabels. Cognitive bias is the phenomenon in which the model persists in mispredictions, caused by overfitting to wrong supervision signals. To further demonstrate cognitive bias, we record the number of pixels mispredicted by the MT method and our MCF method during training, and show visualizations of cognitive bias for both models. As shown above, both the area and the number of mispredictions of MCF decrease compared to MT as the training progresses. Based on the above analysis, we propose a new mutual correction semi-supervised medical image segmentation framework based on the MT-like approaches. Specifically, in order to increase the variability of the model and make full use of the potential of multiple subnetwork architectures, we utilize different structure subnetworks instead of shared structure subnetwork architectures, and change the update method of the parameters from EMA to independent update. Meanwhile, combined with the characteristics of medical image datasets, dynamic pseudo-label generation is proposed to dynamically evaluate the performance of subnetworks, and select a subnetwork with better performance as a pseudo-label generator. Now we describe the process of MCF. The input data in the semi-supervised learning scenario contains a small amount of labeled data and a large amount of unlabeled data. Labeled data is fed into two subnetworks with different structures to obtain prediction results. Then, the dice loss and cross-entropy loss are calculated using the corresponding labels. At the same time, the two predictions are fed into the CDR module for mutual correction learning. Specifically, we utilize the prediction masks to find out the difference in predictions of the two subnetworks and regard them as potential biased regions. To guide the network to further review these regions, a rectification loss is computed using the corresponding labels. The rectification loss is designed as MSE loss in this work. Unlabeled data is also fed into two subnetworks with different structures to obtain prediction results. Then we utilize the DCPLG module to dynamically select subnetworks to generate pseudo-labels. Specifically, the dice loss on labeled data in the same batch is used as a metric to select a subnetwork with better performance as a pseudo-label generator. The generated pseudo-labels are combined with predictions from another subnetwork to compute an unsupervised loss. Therefore, the total optimization loss consists of 3 supervised losses and 1 unsupervised loss. We validate our model on medical images from 2 modalities, MRI and CT, respectively. The LA dataset contains 103D gadolinium-enhanced MRI images, and experiments on this dataset show that our method achieves the best results compared to the comparison methods. especially on the distance-sensitive metrics 95 HD and ASD. From the visualization results, it can be found that compared with other methods, the segmentation result of MCF has a higher overlap rate with the label, resulting in fewer false segmentations and more details. Pancreas segmentation is more challenging than left atrium segmentation. Therefore, we further validate our method on the pancreas dataset. Experimental results show that the accuracy of pancreas segmentation is much lower than that of left atrium segmentation. But MCF still achieves the best results among the four metrics. The visualization results show that MCF obtains more accurate segmentation with smoother and clearer edges than other comparison methods. The other comparison methods are prone to discrete mispredictions and small protrusions or depressions in the edges. We performed ablation experiments on various parts of the MCF. The results show that each component contributes to the result. We also conduct ablation experiments on the type of correction loss and the choice of hyperparameter beta. It can be clearly found that there are some wrong predictions that always exist during the training process of these baseline networks, and CDR helps the network correct these errors. This confirms our hypothesis that although the network has a strong learning ability, they easily fall into their own biases. Moreover, CDR reduces out-of-body discrete errors and makes edges clearer. Experiments demonstrate that DCPLG reduces model overfitting to cognitive biases compared to consistency regularization. In this work, we propose a new framework called MCF for Semi-Supervised Medical Image Segmentation, which enables the network to be aware of its own mistakes and perform bias correction through inter-subnet interactions. The CDR takes the difference predictions of the subnets as potential bias areas and guides the network to review and correct them. The DCPLG is used to dynamically select pseudolabel generators to improve the quality of pseudolabels.